this window.
You can start. Okay. It's working. Network open. Okay, good. Let me double check one thing. Yeah, it's already recording. Okay. Good morning, everybody, and thank you for your attending this English event. He has been here for 20 years, 6 years.
6 years.
Yeah, and he's jointly worked with Dr. Lan together. We have many kind of fruitful results, and today is her show time. Okay.
Okay, so good morning, everyone. I'm Kai-Chu Tsai, and my topic is using the two methods to minimize the end-to-end latency in the satellite-terrestrial networks. And these two methods are machine learning and distributionally robust optimization. First of all, I will give you a quick introduction about what is integrated satellite terrestrial network. Then I will show you my fieldwork during my PhD. And in the end, the conclusion will be provided, and I will show you my potential future works. And satellite technology has come a long way. And since the first launch of the first artificial satellites, Sputnik 1 in 1957, over the decades, it changes the people communicate. And in recent years, satellite networks have become important, and it can provide global coverage and extend the limited terrestrial networks. Besides, the satellite network can offer continuous communication, disaster management, rapid deployment, and faster data transfer. By combining the terrestrial and satellite network, we will have a new communication infrastructure, ISTM. So people living in remote and isolated areas can now get online, and they can watch videos and chat with friends without any annoying delay. And a great example use case of ISTM is 6G. And it can provide global uninterrupted connectivity. And because 6G receives signal both from the ground and space, so it is very good at precise allocation applications, such as the autonomous vehicle driving, precision agriculture, and emergency response system. And with low latency and high transmission rate, 6G is also good at the AR, VR, and MR. And there are some challenges in ISTM. The satellites move in a higher speed in comparison with the Earth. So the link between the ground and the space will be interrupted. The network topology is dynamic. It will cause the end-to-end routings, link management, the handover processing problems. The buildings and maintaining satellite, the costs are really high. And in ISTM, we have two networks. One is terrestrial networks, and the other is satellite network. So how to integrate these two different networks and find a best protocols on it is also a challenge. And in this research, I mainly focus on the end-to-end routing part. And there are some uncertainties in ISTM due to the high mobility of satellites. And the first one is varied coverage and connectivity. It will cause the handovers and intermittent communication links problem. And the second is changeable propagation delay and signal quality. Double shifts will introduce the uncertainties in signal reception. Due to the ionosphere perturbations, the communication between the ground and space will be affected by the space weather. So in the previous slide, we talked about there are some uncertainties in ISTM. then we are thinking about which model or which method can solve the uncertainties problem. And in general, we have three uncertain optimization optimization models. And the stochastic programming, distributionally robust optimization, and robust optimization. And in my PhD, I mainly focus on the DRO. And let me give you some details about the three uncertain optimization model. The first one is SP. And in SP, we will collect all the data and use the historical data to build up the random parameters probability distribution. Then in SP, our goal is to find an action that can minimize the expected cost based on this probability distributions. And the second uncertain model is RO. So in RO, we don't know the actual random probabilities, the distribution of it, but we know the range of it. So here for the example here, we want to know how many vehicles are on the road. And we just know that the number of vehicles is within the range from 100 to 600. And this range forms the uncertainty set. So in robust optimization, our goal is to find a division and that can minimize the maximum possible cost under this uncertainty set. And the last one is DRO. And in DRO, not only the random parameters are uncertain, but also the probability distribution of it is uncertain. And we can see an example here. So this probability distribution shows the number of vehicles on different dates. So just like yesterday, we have the eclipse. So most of the people went to the Dallas. So the number of vehicles in Houston will be lower than before. So, and on the cloudy days, most of the people will go outside to play. So, the number of vehicles the probability of it will be like 300 to 400 here. And in DRO, we will have multiple different or similar probability distributions. And those distributions form the ambiguity set. So in DRO, we want to find a division, and that division can minimize the worst case expected cost over this ambiguity set. And this today's presentation, I will cover three work. And those three works aims to minimize the end-to-end latency. And in the first work, I will consider the data delivery in satellite network. And the DRL method is proposed to solve the minimal end-to-end latency problems. And the last two work, the scenarios will be the ISTN. So not only have the satellites, but also have the terrestrial network. And in work 2, the DRL method as proposed. And in work 3, I use the DRO models to model the end-to-end latency problems in the ISTN. And let's start with work 1. And the topic is using the deep reinforcement learning to solve the multi-commodity flow routing problems in the real satellite networks. And from literatures, we can see 2 examples. In reference 1, the optimal end-to-end latency is found by the Q-learning method. And in reference 2, a multi-agent RL was proposed to find a routing path under the tolerable end-to-end latency. And the good thing is both works can reach the goal to find the minimal end-to-end latency path. But it is hard for the Q-learning methods to handle the large state space in the complicated networks. And also, it is also difficult to manipulate several agents in RL. So in work one, I consider a single agent RL, and this agent can make many actions at the same time. And I propose the RL satellite routing strategies to handle the routing problems in the LEO satellite networks. So let's start with what is the LEO satellite network. So in LEO satellite network, we have a bunch of satellites above the Earth, and each satellite will follow each other in lines, just like the trains on tracks. And the tracks or the lines are side by side. And the satellite will keep moving because we want to check the position of each satellite. So here we use something like the time-selected structures to capture the position of each satellite. So the total time can be divided by t time slots, and each duration is tau. And here we also think that when we switch to a new time slot, the topology will also switch to very quickly. And we can model this network topology as an undirected graph GT here. And we will have multiple users on the Earth, and this user need to transmit their requests via the satellite constellations. So the request for each user can be denoted by this notation. So it means that the request is from the user I as a delta time slot, and its request, it covers the request is from which source satellite and need to be transmitted to which target satellite. And we also need to note how big is this request. So let's see the animation of that. So the first time slot, the first user and second users that put their request on the two source satellites, here and here. And these 2 points are the corresponding destination satellite of these two files. And at the second time, the third user put their request on the satellite. And that is the corresponding destinations of the third user's request. And at the same time, the first user maybe forwards their request to the satellite. And the first users at the time slot to forward their request to the satellite. So we can see that in our satellite constellation, we will have multiple files, and each of them can be generated from different sources and can be transmitted to different destinations. And this kind of problems is one of the multi-commodity flow routing problems. So in the multi-commodity flow routing problems, we will have multiple events, and it needs to be transmitted from certain source to destinations. So it is similar in our scenario here. And our goal is to transmit all the tasks from the source to the destination satellites with the minimal delay. So the metric I consider here is the delay. So I use these equations to define the delay to transmit certain file from satellite U to V. And if this file is already arrived at the destination, so there will be no delay because it is already arrived the target. But if the file is on the way to the destination, it will have the routing delay or the waiting time. And here the routing delay includes the propagation and transmission delay. And alpha and beta are the two binary division variables here. And it indicates whether a request is forwarding from one satellite to another satellite, or the request is just remain at the current satellite. And here is the problem formulation. We want to routing all the requests from the source to the destination with the minimal delay. And in order to reach this goal, we need to follow the following constraints. Like, so the two constraints are the decision variables I mentioned previously. And we also need to know need to satisfy the link bandwidth, buffer capacities, and the flow imbalance constraint functions. And because this formulated preference as pure binary integer programming, it is NP hard. So in the next part, I will show you how to use the RL method to solve it. And in RL, we will have the agent and the environment. And the agent here is the satellite operation centers, and it knows all the information in our environment. And the environment here is the satellite constellations. So we know the agent and the environment. The next part is to define what is the state and what is the action and the reward. So we can let the agents learn a new mission by interacting with the environment. And the states here, we need to record all the information in the satellite network, including the location of the satellites and the available storage of each satellite, because in the constraint functions, we consider the storage availability for each satellite. And for the request part, we also need to know the request is on which satellite. And because we need to know the latency of the transmitting request, so we also need to know how big is the request. And the next thing is action. So the agent needs to make the action, and this action is how to forward the request from the source to the target satellite. And for each request actions, it consists of two parts. And one is to let the request stay at the current satellite, and the other is forwarding the request from the current satellite to the neighboring satellites. And then after defining what is the state and action, and the next part is reward. So at each time slot, the action will get a reward after it taking the action. And if the agent decide to let the request stay at the current satellite, then it will receive a reciprocal of the waiting time as a delay, as a reward. And if the agent move the request from one satellite to another satellite, then it will obtain the reciprocals of the routing time as a reward. And in order to differentiate the reward by the agent taking the same action at different states, so here the extra reward is considered like the beta and gamma here. And those values are decided by the distant relationship between the current next hub, the rest of next selected satellites, and the destination satellites. And I assume that once the request is transmitted, it will be forwarded to the next hub. It will not remain on the link. So the transaction function here only involves the storage availabilities in each satellite. So we can see that the next time's available satellite storage will be the current time available storage plus the variation of the flowing task. And multi-step learning, it combines the benefits of the one-step temporal difference learning and multi-column method. So it can allow the agent to learn fast. And in our proposed DRL, we combine the multi-step learning with the DQM method. And here is those functions for our proposed method. And with those functions, we can train the agent and let the agent learn how to forward the request from the source to the destination. And here is the simulation result. And I compare the proposed methods with the shortest path algorithm here. And in these figures, different numbers of satellites are deployed in the satellite constellation. And we can know that if we deploy more satellites on the on the network topologies, loss time is required to transmit the same amount of the files. And here we can also know that because the shortest path only makes the decision based on the distance between the two nodes, the two satellites. So it will have a local minimum solution, and it will affect heavily by the number of satellites deployed on our satellite topology. And these figures I considered what will happen if we have multiple users on the satellite topology. And here we can see that if more users want to use the satellite constellation to forward their requests, more time is needed. And in work one, I consider the data delivery problems in the satellite constellation. And this problem can be formulated in multi-commodity routing problems. And I propose a single agent DRL methods to find the minimized data delivery path. And in the simulation results, the proposed method requires less time to complete the same task in comparison with the shortest path algorithm. And here, I already talked about the work one. And in work two, I further consider the terrestrial network in our scenario. And the topic is integrated satellite terrestrial network routing using deep reinforcement learning. And from the literatures, we can see two examples. And in reference 3, the authors, it will calculate numbers of the hubs are needed from the source to the target user equipment. And in reference 4, it optimize or it find the optimal routing path. But it didn't consider the offloading and downloading latency between the two segments, the ground and space segment. And also they just assume that the only way for the ground and space to have a communication is through the satellite gateway. So in work 2, I assume that each mobile device, they can transmit their signals or send their data to the satellite directly. And here I use the multi-step DRL method to solve the data delivery problems in the ISTM. And here is my system model. We will have lots of users, all users on the ground. In the satellite constellation, we will have M satellites. And each satellite flies at an altitude edge with inclination degree alpha. And we have lots of users, and they need to use the satellite constellations to do the data delivery. So this notation is used to record the data size for each user's request. And here we also make another assumption that under this condition, there will be no serial systems or other network facilities. So the satellite constellation are the only communication infrastructure that can make these two users to have a communication or send their data. And let me go into the details about our system model. So we will have the ground segment, and on the ground, we will have the source and destination user equipment. And besides here, we make data one co-min. So
hello, Dr. Wang. Yeah.
right. No, Martin. So go ahead. Okay. So here I make an assumption that we will have the user equipment. At least user equipment, they need to transmit the request. There is always at least one satellite can provide the communication service for it. And in the spec segment, I consider the Worker Delta constellation here. And in Worker Delta constellation, it has around 1,500 satellites in the space. And all the satellites are at 550 kilometers. And the interesting point for the Worker Delta constellation is that for each satellite, there will be always 4 neighboring satellites. And by combining the ground and spec segment, we can take out the physical ground specs link. And because I guarantee that for each user, they need to use the satellites to have the communication. So there's always at least one satellite can provide the service for it. So the set will be larger or equals to 1. And I consider the data delivery finding problem. So let me introduce what is the latency in this scenario. And the first one is the uploading delay. And in uploading delay, the user can transmit their task from the ground to the satellite. And the routing delay, it concludes the transmission and propagation delay. And once the request is uploaded to the satellite, then there will be the routing delay within the satellite constellation. And if the satellite can access to the target user equipment, then there will be the downloading delay from the space back to the user equipment. Then, I want to formulate a problem and I can deliver all the tasks from the source to the target user equipment with the minimal delay. So in the objective functions, it will include all the task delivery delay. And for each request, it will have 3 kinds of delays: the offloading delay from the ground to the space, and the routing delay in the satellite network, and the downloading delay from the space back to the ground. And the deletion variables here, we will have 4 deletion variables. And the first 3 are used to indicate whether this request should be uploaded by from the source satellites to which, from the source user equipment to which satellite. And the second deletion variables, it decides the text should be forwarded from which satellite to which neighboring satellites. And the third deletion variables indicates that, okay, so this 4 should be transmitted from which satellite to the target user equipment. And the last deletion variables, it indicates whether this file should be remained at the destination satellite, because the total observation time is larger than the data delivery time. And here is the problem formulation of work 2. The objective function as the total latency for transmitting all the requests. And we want to route all the requests with the minimum delay. And in order to reach this goal, we need to satisfy the following constraint function. Just like the previous mentioned, we restrict at each time the request can only select one hop. And it needs to follow the flow imbalance and constraint functions. And because this problem is flow binary integer programming problems, and so I use the DRL method to solve it. And the agent is still the satellite operation centers, but the environment here, we not only have the satellite constellation, but we also have the user equipment on the ground. So in the state, we will have the location of each satellite, and we also need to know the text is on which satellite and the text need to be forwarded to which target user equipment and how big is this task. And we also need to know the locations of the source and target user equipment. And the agent need to make the action for how to transmit all the text from the source to the user equipment. And because the worker delta constellations, there will be always full inter-satellite link for each satellite. So the action space for the agent will be only 4. And the first action is to forward the task to the upper satellite in the same orbit. And the second action is to deliver the task to the lower satellite. And the third and the fourth action is to transmit the task to the left orbit. And the last one is to the right orbit. And then the next part is about the reward. And the reward here, it is a reward for the agent if they make a up, down, left, right actions, and what is the benefit for the agent can get. And because we have 3 different one have latency, the uploading, downloading, and the routing within the satellite constellation. So the rewards can be also be divided into 3 parts. And the first one is if the agent make a decision and the task can be uploaded from the ground to the space, then the agent will get the negative offloading delay as a reward. And when the task is on the satellite constellation, so we need to route the task, we need the satellite network. Then the agent will get the negative routing delay as a reward. And because we want to vary the reward at different time slots, so we adopt the exponential decay reward here. And under this setting, we can also ensure that transmitting all the tasks to the test from the source to the target user equipment as quick as possible. And once the satellite can access to the target user equipment, then the agent will get the negative routing delay and negative downloading delay as a reward. And here is the simulation result. I compare the proposed method with the random approach. And here we can see that when more users want to use the ISTN to deliver related tasks, and more time is required. And because the random approach, it just make a decision without any rule. So when more users want to use the ISTN, the total number latency for the random approach will affect heavily than the proposed method. And here I put these 2 methods under different traffic loads, light, medium, and high. And in light medians, the transmitting data size is we need 1 to 5 megabytes. And median, it is 2 to 6. And high, for the high traffic loads, the data size ranges from 3 to 7 megabytes. And here we can see that when the data size increases, the random approach, it needs lots of the total latency it requires more, because random approach it just makes the decision without any unpredictable manner. And in work 2, the data delivery preference is considered in ISTN, and I propose the multi-step DRL method. And in the experiments, we can know that the proposed method requires less latency when compared with the random approach. And I conclude the work 2, and in work 3, I consider some uncertainties in the ISTN. And the topic is DRO for the integrated satellite-terrestrial routing. And in the literature, there are two works, the reference 5 and reference 6. And both of these works can find the data delivery path, but these two works, the only way for the space and ground to have the communication is through the terrestrial satellite terminals, and the coverage area is very small. And in order to enhance the communication range of the terrestrial terminals, so here I put the TST on the vehicles. And I also assume that the user equipment can have a direct communication with the satellites. And here, because I have the vehicles in my system model, and we don't know the actual moving direction of the vehicles. So the latency related to the vehicles is uncertain. And in work 3, I propose the DRO model to handle the uncertain delay due by the vehicles. And here is the system model. And we have two cities. One is called source city and another as destination cities. And on these two cities, we will have multiple user equipment and also have the TST on vehicles and on buildings. And each user equipment, they will have the information like the text messages or the videos and the photos, and those informations needed to transmit it to the corresponding target user equipment, and only through the satellite constellations. So let me show you what is the possible data delivery path. So this mobile device, it has a text message, and it forwards the text message to the TST on vehicles, and the vehicles we route these to the satellites, and that will make the routing within the satellite constellation. And once the satellite can access to the target user equipment, and the satellite transmits the file, the text message to the target user equipment, and with the help of the TST on building. So the red arrow here shows the possible routing path in this scenario. So based on this system model, we can divide the data delivery path into 3 parts. And one is the uplink path. It is from the ground to the space. And another will be the routing in the satellite network. And the last one will be the downlink path. It will deliver the task from the satellites back to the target user equipment. And let me give you the details about the uplink delay. So the direct uplink delay, it is the first one is from the user equipment to the vehicle, and then to the route, and then to the satellite. So here is the routing delay from the user equipment to the TST on building. And the second one is from building to the satellite. And each routing delay includes a propagation and transmission delay. And the next one is user equipment can transmit their message to the satellite directly. So here we only have 1/2 latency here. And if we use the vehicles to upload our task, and the perfect way is from mobile device to vehicles and then to the satellites. And here is the corresponding routing delay. But because we don't know the actual moving direction of the vehicles, so if the vehicles move out of the communication range of the user equipment, then we need to reroute our task from the user equipment to the satellite. And the first way is from building to reroute it from building and then to satellite. And the second is just retransmitted from the user to the satellite directly. And both of these methods, because we need to reroute the task, so it will have the head of code here. And we can also know that the latency related to the vehicles will be within a certain range, so it is uncertain latency. And for in a when we need to download the file from the satellite to the user equipment, we can also analyze the downloading delay in a similar way. And the first one is from satellite to the building and to the user equipment. And the second one is just directly transmitted from the file from the satellite to the user equipment. And same thing happens if the downloading delay also use the TST on the vehicles, and the perfect path is from satellite to vehicle and then to the user equipment. But if the satellite moves out the range of the satellite, if the vehicle moves out of the range of the satellite communications, we need to retransmit the text from the satellite to the user equipment. So here, one possible way is from satellite to building and then to the user equipment. And this is the corresponding routing latency. And another way is to retransmit the task from the satellite to the user equipment. And here we can also know that because we don't know the vehicle's moving direction, so the downloading latency related to the vehicles will be also within a certain range. So it is also uncertain. So based on the previous slides, we can know that the vehicle latency is uncertain. So here I use the word system ambiguity set to set up the ambiguity set for the uploading and downloading latency related to vehicles. And here, let's talk about the problem formulation in block 3. For each request, because it has been passed to in the data delivery, and one is the uploading delay from the ground to the space. And then it is the routing delays within the satellite constellation. And the last part is the downloading delay from the satellite back to the user equipment. So the objective function is the total routing delay for transmitting all the requests. And the binary and the decision variables here, and the first two are to decide we need to use which path to upload our task from the user equipment to the satellite. And the third and fourth decision variables, it indicates we need to use which downlink path from the satellites back to the target user equipment. And the fifth constraint, it is about the next task within the satellite constellation. And 6 and 7, it indicates if the request need to be stored at the current satellite in the satellite network, or if the request can remain at the target user equipment permanently. And in order to reach the minimized end-to-end latency, we also need to follow in to let the request be taken only one action at each time slot. And we also need to follow the outflow-inflow imbalance and flow conservation. And the interesting point in this problem formulation is because we want the users to use the vehicles to upload their task mode. So we have a restrictions on the number of users can use the building to upload their file. And this problem formulation, it is very big and have lots of constraint functions. So how to solve it? And the first thing, we deal with the maxima expectation form, and we consider the two ambiguity sets here. The ambiguity set for the uploading and downloading latency, and we transform this problem by the duality theorem, and it can be into a minimized problem. And after we get this minimized problem, then we can combine it with the previous constraint functions. So at the end, we can get this reformulated problems, and it is much more manageable and it is convex form. So we can use the regular or the classical solver like the Google or Cplex to solve it. And here is the simulation result. So this is the green, the orange is the proposed DRO model, and I compared the DRO model with the rest of the two uncertain optimization models. And here, because we know that the SP, it knows the actual probability distributions of the vehicle latency. So it requires less time to transmit the request. And in RO, because it only knows the range of like uncertain random parameters. So it is much, so RO makes the decision very conservative. And DRO, it is the method step between these two. So the latency for the DRO is within the SP and RO model. And here, because we know that in DRO, we have the ambiguity set. And in this figure, I investigate the total latency computed by the DRO will be influenced by the ambiguity set or not. And here, so theta1 and theta2 are the size amplification factors, and it can determine how large is this ambiguity set. And under these settings, the ambiguity set theta2 is larger than theta1. And we know that because if the ambiguity set is large, and it will be the uncertainties of it is also larger. So the total latency for the larger ambiguity set, for the DRO model, it will very close to the RO model. And if the ambiguity set is small, which means the uncertain probabilities distribution, it will be much closer to the actual probability distributions. So the smaller ambiguity set, the result of it will be very close to the SP model, which has the actual probability distributions. And in work 3, and I consider because we have the vehicles on the ground and the latency, the uploading and downloading latency related to the vehicles is uncertain. And I models those uncertain uploading and downloading delay in the Western ambiguity set. And I propose the DRO model to handle the uncertainties in ISTM. And let me show you some potential research based on my dissertation. So in work 3, we know that we can use DRO to handle the uncertainties in ISTM. And so my thought is, if we can use the RL to also handle the uncertainties in it, so here, usually we know that the agent, it takes the random approach first to explore the environment, and at the end, it uses optimal policy to make a decision. So here, in this DRRL method, so this point is the optimal policy, and I say that an ambiguity set based on this policy, and the point within this cycle is the possible policy the agent can take. And so every step, and and we can choose the worst case policy to train the agent. And under these settings, we want to see, we hope we can see that the agents can build more unsafe environment in the new testing case. And another potential work as quantum computing, and because we know that quantum computing is recently developing, and all the data delivery problems in my presentations are all pure binary integer programming problems. So another possible work is to use the quantum solvers to solve the data delivery problems in ISTM. And another potential work is we know that the most important part of the RL is the agent. And right now, we use the neural networks, the fully connected neural networks, or the convolutional neural networks to build out our agent. And great neural networks is very good at knowing the relationship between the nodes and the links in the topology. So another possible work is to upgrade the agent's neural network from the general neural network to the graph neural networks. And also we conclude the potential works, and let me give you some key points I covered today. And first, I talk about the importance and challenges in ISTM. Then I introduce 3 data delivery problems in the satellite network and the ISTM. And all of these work are to minimize the end-to-end latency. And in work 1, I propose a single agent RL and to have a data delivery mission in the satellite networks. And in work 2, instead of just consider the satellite network, I also combine the satellite network with the terrestrial network. And I use the DRL methods to solve the end-to-end latency problems. And in work 3, we have the vehicles, so the problems have the uncertainties in it. And I use the word system ambiguity set to model the uncertain uploading and downloading delay related to vehicles, and use the DRO method to handle the uncertainties in ISTM. And this is my publications. And thank you.
You can stop recording.